Aloha. My name is Benjamin Bowe, and I am a graduate student here at the University of Hawaii's Institute for Astronomy. I study the sun's outer atmosphere, which we call the solar corona, and I'm interested in how the solar wind changes as it propagates from the solar surface through the corona and into interplanetary space.
I work with a team of astronomers and engineers to observe the solar corona during total solar eclipses when the moon completely blocks out the sun. At each eclipse, we observe the corona with spectrometers and cameras, custom built to observe emission from ions at specific colors. So far, I have traveled to Indonesia in 2016 and Nebraska in 2017 to observe a total solar eclipse. But our team's leader, Professor Shadia Habal, has been observing eclipses for almost 3 decades and producing groundbreaking scientific studies about the physics of the solar corona. You might wonder why we go through so much trouble to travel around the world to observe total solar eclipses. Well, the answer is that the corona is only observable all the way down to the solar surface during a total solar eclipse. Even with a small telescope, we can easily see the solar surface or photosphere, but we cannot see the corona with this telescope because it is so much fainter than the bright solar photosphere. During total solar eclipses, however, we can observe the sun all the way down to the solar surface and outward to 3 solar radii, with incredible spatial resolution and spectroscopic capabilities. Here is a more complete picture of the sun, showing both the higher density and colder photosphere at around 6,000 Kelvin, compared to the much lower density and hotter solar corona at a couple million Kelvin. Not only is the corona much hotter, but it has a very steep density gradient going outward from the sun. It drops several orders of magnitude in the first few solar radii. The combination of the high temperature and a steep density drop creates a pressure which pushes particles away from the sun with enough force to overcome the strong gravitational field. This outflow of particles is what we call the solar wind. In the low corona, the density will be high enough that particles will be colliding with each other quite frequently. This will allow heavy ions, such as iron, to lose or gain electrons, processes that scientists call ionization and recombination. Far away from the sun, the density will eventually become so low that no particles are near to one another, and so they can no longer collide. They will then be unable to change the total number of electrons that they have, or their ionization state. The distance at which ions can no longer change state is called the freeze-in distance. It has been modeled in several publications, but it has yet to be observed in the corona directly. In my paper, which has been recently accepted by the Astrophysical Journal, I used data from the 2015 solar eclipse in Svalbard, Norway, to measure the freeze-in distance of 2 ionization states of iron. Our team took images with filters centered on emission from 2 different states of iron, namely iron 10 plus and 13 plus. In this hot environment, heavy elements such as iron have their outer electrons stripped off and are left with a highly positive charge. We also took images with similar filters centered slightly away from the emission line. In this way, we could measure the background continuum radiation from the electrons and dust in the corona. We then took the ratio of the 2 images, that is, the emission from the ion divided by the background continuum emission. This allows us to measure the change in the ion density with respect to the electrons. The coronal density as a whole is decreasing, but the relative density indicates if the ions are changing state. We calculated this ratio along different structures in the corona, which will go on to form the solar wind. We observed the change in the ion to electron density ratio as a function of distance and measured the distance where it became flat, that is, where they ceased to change ionization state. We found in general that the 2 ions did not freeze in at the same location in the corona, and that the freeze-in distances varied a great deal depending on the underlying structure. With the measurement of both freeze-in distances, we were able to distinguish different regions in the solar corona. The coronal holes, which tend to be dominated by open magnetic field lines, had the lowest freeze-in distances, with the colder ion, iron 10 plus, having a slightly larger freeze-in distance than iron 13 plus. This order is reversed in the quiescent streamers where bound field lines are more common. The passage of a coronal mass ejection, or CME, made the freeze-in distances have a similar behavior to the coronal holes, except with a much larger overall freeze-in distance. Prominences in the eastern corona also had some dynamic effects that raised the iron 13 plus freeze-in distance beyond what it was in the quiescent streamers. Finally, in the northeast, there were bound field lines that prevented plasma from freezing in within our data. Most likely, this part of the corona had a much larger freeze-in distance than anywhere else.
Of course, there is still much more work to be done. We do not yet fully understand the cause for the variation in the freeze-in distances, and we only looked at a single snapshot in time with 2 different ions. In the future, we plan to look at additional ions from many eclipses in order to build a more complete picture of the physics in the solar corona. In the meantime, go out and enjoy the sun.
Mahalo for your attention. For more, check out my website at www.ifa.hawaii.edu/users/BBOE. Thanks.